Alright, so today we're doing more three-letter rates. It's again the exact same idea as what we were doing before, but we're encountering problems that require us to use trig to solve them. So before, our typical types of equations, we dealt with Pythagorean theorem, we dealt with volume, surface area. Was there anything else we used? Yeah, we had circumference in there. So those were typical types of problems that we had. Now we're dealing with problems that are definitely triangles, and oftentimes we'll ask for something about the angle, which kind of forces you into using trig. Okay, so for this first example, we have a camera that's mounted 3,000 feet from the Space Shuttle launching pad. Maybe it's SpaceX, maybe it's NASA, we don't know. The camera needs to pivot as the shuttle is launched and needs to keep the shuttle in focus. The shuttle is rising vertically at 800 feet per second. When it is 4,000 feet high, how fast is the camera to shuttle distance changing? Okay, so we've got a rocket. Looks like a house with a skirt on or something. And we have a camera is mounted 3,000 feet from that launch pad. I'm going to move this. Okay, so we know that this distance here is 3,000. Is it feet? The camera needs to pivot as the shuttle is launched. It needs to keep the shuttle in focus. So our shuttle is going up, 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 up. And our camera is staying trained on that. Okay, so our shuttle is moving up. Our rocket is going up. And didn't tell us anything about it. Oh, the shuttle is riding vertically at 800 feet per second. So we do know that this rate is 800 feet per second. And then they ask, okay, at the moment in time when it's 4,000 feet high, how fast is the camera to shuttle distance changing? All right, I'm going to go and put in some variables here. I'm going to call this x, call this y. What did I choose? Sure. Z sounds good. Okay. So when it says how fast is the camera to shuttle distance changing, that indicates we're looking for a rate there. But what variable is it referring to? Z, good. The camera to shuttle, because remember the shuttle is going up. Alright, so let's go ahead and do this. So far, it's pretty much like normal. Let's take a look at what we know. Alright, so I know that y is changing, z is changing, is x changing? No, x stays at fixed amount, so we know x is at fixed amount of 3,000. And they gave us that our height of our rocket, so dy dt equals 800. Alright? And we want, so dz dt, specifically when 4,000 feet high. So what variable is that going to be? Good. And y is 4,000. Okay. So this first part is just like we've done before. No trig has been involved yet. So I want you guys to go ahead and set up and solve this. Feel free to work with the person next to you. And feel free to use your... Do we need a calculator for this one? You don't really need it, but you can use your calculator if you like this one. Again, you're welcome to talk to one another. Yes. Winter packets are not graded yet. No, it's graded for accuracy. That's what it said on. For correctness. What was your guys' equation you used?
So x y z
Good, so our Pythagorean theorem. Okay, good, continue on. I'm going to go ahead and start it up here so that you guys can even check. That's 4,000. I apologize. Great question. My x value, that distance is not changing at all. So as the rocket goes, it's still horizontally 3,000 away from it. My y is a changing value. That distance is changing. Z, it is a changing value.
So after you take the derivative, then you can plug in the y.
Yeah, so after we take the derivative, then we're saying, all right, pause. Let's plug it in at this particular point in time. Did I see another? Okay. What's my z value when y is 4,000? 5,000. Raise your hand if you did that without a calculator. Good, because what type of triangle is it? It's a 3, 4, 5. Good. So it's a Pythagorean triple. It's a 3, 4, 5. Since this was, it's basically not what is there a word equivalent for double but 1,000? So multiplied by 1,000 on each of these, so this would just be. Okay, good. Wonderful how geometry just keeps going back. Okay. Questions so far before we throw out what the answer is? Okay, what did we get for dz? 640, and what's our units? Feet per second. Okay, so what we're saying is, all right, 3, 2, 1, 0, blast off, rocket starts going up, and the second that it gets at 4,000 feet high, we know that this distance here is changing at a rate of 640 feet per second. And we see that it's positive, which makes sense because as it goes up, our hypotenuse there is going to move. Okay. Questions with that? We should actually write out a nice statement for it. The camera to shuttle distance is changing to shuttle distance is changing. Or you can even say is increasing at that rate. That would be fine. At a rate of 640 feet per second. Okay, so again, this is just like we did before, but now let's take a look at this. So in this problem, how fast is the angle of elevation of the camera changing at this particular moment in time? Ooh, angle of elevation. We got our first dose in geometry and then the second dose in pre-calc. What is that angle of elevation? Good, so it's from the ground looking up. So would you guys agree that it is this guy here? Okay. So we want to know, because that makes sense. As the rocket goes higher, the angle of elevation is changing. Would that be increasing or decreasing? It'd be increasing, good. So we would expect a positive rate for that. All right. So says how fast is the angle of elevation of the camera changing? So we're looking for d theta dt, the change in angle with respect to time. And since this is a function of theta, the only way that we can relate that theta is through using trig. All right. So a reminder of our trig values here. So sine of theta is opposite over hypotenuse. Probably a good thing we chose z. Good work, guys. So opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay. So let's go fill in what information we do have for each one, and figure out which one's going to be the best to use. Because it's like we're starting a new problem, if you would. We want to know our angle of elevation change, so we want to know d theta dt. So we need to use one of these because that introduces theta into our equation. So one of these is going to be the equation that we use, take the derivative of and plug in. Okay, so before we use Pythagorean theorem, now that we have to deal with angles, we need to bring in trig. So let's take a look. So again, we're looking at our information given to us. So for sine theta, is my y, well, that was changing, so we have to leave that as a variable. And my z is also changing, so we would have to leave that as a variable. All right, so for cosine, so cosine of theta, adjacent, well, guess what? X is a fixed value, so we can go ahead and throw that guy in. But my z is changing, so leave that as a variable. And for tangent here, so y is changing, leave that. X is fixed, so we leave that. Which one do we know without a doubt we should not use? Sine. Yeah, sine's got too much going on there, right? We don't know y, we don't know z. And if we think about it, when we take the derivative, we would have d theta dt, dy dt, and dz dt. Okay, well, I've got dy dt. Not much more. Okay, so we know we definitely don't want to use that. Now let's take a look at cosine and tangent. For cosine, I don't know z, and when I go to do the derivative, I would have d theta dt. Just fine, that's what we're looking for. And I would have dz dt. Do I have dz dt? We found that, right? Okay. Yes.
Why are we using 5,000 for z?
Why aren't we using it?
Yeah.
So we can put that in once we take the derivative. But before we take the derivative, we would have over here, we would have dy dt and dz dt, and we don't know dz dt. Although actually we did just solve that, so I guess technically we could use that one there. So again, that 5,000 is after we've taken the derivative, then we can plug that information in. Yes?
Do you know you would do b for like x, y, and z, or where we put those, like x for y and z?
So our setup would be different if we did like x over here, y there, and z there. Then our setup for sine would be different for each of these. All right, so for cosine, again, we just found dz dt because we're looking at that same moment in time. So we could use that information and do it that way. All right, tangent, we would have d theta dt and dy dt. Do we know dy dt? Yeah, that one was actually given to us in the very beginning. Okay, so if we had not done problem A, our only option would be tangent, right? Because that's the only thing that has been given to us. But since we did problem A, we now know dz dt, so we could have used one of these others. But let's just go ahead and use our tangent, since that's what was given to us. And let's figure out what is the change in theta with respect to time. I get the feeling I should have written smaller there. Okay. So again, our theta is changing. We can't put in a constant there, and our y is changing. So let's go ahead and do our derivative. Ooh, gee, those derivative traits are important. What's the derivative of tangent? You guys make my heart so happy. Good. Secant squared theta d theta dt, because we have to then take the derivative of the inside, and derivative of theta is 1 d theta dt. All right, then over here we get, let's see, 1 over 3,000 dy dt. Are we all okay with that derivative?
Sometimes we can't use new to find out the derivative, but we didn't use like 4,000
So,
like we said we can't use 5,000 to be found after the derivative.
so we can only use the 5,000 after I've done. So like right now I can't put it in, but once I do the derivative.
We didn't use the derivative sign.
Right, but what we're saying is, so this 5,000 is coming from when it says when x, or when y is 4,000. So we're saying this is our scenario, our generic scenario. And then we're pausing the clock the moment that the rocket is 4,000 feet off the ground. We're saying at that one time. Now, does that make sense? Yeah. Mm-hmm. All right, are we good with this derivative here? Okay. So again, we want to find d theta dt. Okay, so let's substitute in the information we do have. Do we know what theta even is? No. But we do know the triangle that it's dealing with, right? So let's, again, the triangle we're working with here. Just drop here. I know x is a fixed 3,000. And what's that we're doing again? We're finding this specifically in when what? What point in time are we looking at? That same moment, right? So we're still looking at that same moment when y is 4,000 and z is 5,000. We already did that work. Okay, so we're pausing at that moment in time. Y is 4,000 and z is 5,000. So although I don't know theta, could I find secant of that? Yeah, I can find sine of theta, cosine of theta, tangent theta, because I have all my sides. Remember, your trig function is just a ratio of the certain sides. All right, what function does secant correspond with? Cosine. Okay, so what's cosine of theta? Ooh, sure didn't tell your shoulder partner real quick. What is cosine of theta? Alright, so we refreshed our memories with the chant, so we talked about finding Nemo here, right? Okay. So cosine of theta is 3,000 over 5,000 or 3/5. Are we all good with that? We're good with that now. Okay. I got a little worried when I heard 4 over 5 or 3. Okay, so again, that's my cosine. So what is secant going to be then? Good, 5 over 3. And we need to make sure we don't lose our squared there. We don't know d theta dt, that's what we're solving for. And then I have 1 over 3,000. And what was my dy dt? 8. All right, go ahead and solve. What do we get for d theta dt? Slow down though. What do we get for d theta dt? What did you guys say? 12 over 1. Good. 12 over 125. Ooh. What are our units for that? Radians. Yeah, so we're looking at the change in the angle. The angle is measured in radians. We're always in radians for calculus. So radians, and what was our time? Good, radians per second. Okay, so the angle of elevation is changing at a rate of 12 over 125, or you could say it's increasing at that rate of 12 over 125, whichever you feel like. I like throwing in that it's increasing, bonus knowledge. Increasing at a rate of 12 over 125 radians per second. So again, same idea as before, but what we have is that the equation that we're using to relate the variables is now our trig. So for this particular one, we chose tangent of theta. And oftentimes you'll be using that trig when you're looking for that angle, or when they're asking them about that angle of elevation. Okay, questions with that? Okay, go ahead and read this next problem. I did not create this. I'm not sure why Brian is wanting to make Sasha fall. But go ahead and read this problem and we'll take it. I think Brenda was like, oh, how dare he? I don't know. Maybe they're brother and sister and she did something to him earlier. That's the way it goes. All right, go ahead and draw a picture to kind of represent what's happening here. Okay, so we have Sasha standing on top of a 12-foot ladder, and it's leaning against a vertical wall. And Brian is mean and pulls the lower end of the ladder away from the wall. So we have this is going away. So that rate, at a rate of 2 feet per second, is that positive or negative? Good, positive. That distance there is increasing. All right, so then it says, find how fast Sasha is falling as the ladder slides down the wall. At the instant, it is 6 feet above the ground. So we have our ladders coming down. And we're looking at the moment in time when it is 6 feet above the ground. What is that 6 feet going to represent? Which variable? How about we throw in some variables? X, Y. Let's go with Z again. Okay, so which variable is that 6 feet representing? Y. Good, Y. So this is when, specifically when Y is 6. Okay, and what are we wanting to find here? How fast Sasha's falling as the ladder goes down. So what rate would that be? dy dt. Okay, so let's go and write out what we know and whatnot. So we've got dx dt given to us. It's a positive 2. We know that z is going to stay that constant 12. And let's see what we want. We want dy dt when y is 6. Okay, what equation do you think we should use? Yeah, Pythagorean theorem. If you're tempted to use trig, just as you set up your trig, look to see if you have enough information for it. If I try to use trig, I would need an angle. And we don't have that when you try to do your derivative, you'd have too many unknowns. Okay, so Pythagorean theorem. All right, so we've got x is changing, so that stays as x. Y is changing. Let's try it again. So that will stay as y. And z is staying the same, so we can go ahead and replace these here. All right, go ahead and do our derivative. We get 2x dx dt. plus 2y dy dt equals 0. We want specifically when y is 6. Looks like we're going to need the x value. So let's see, we have x squared plus 6 squared equals 12 squared. What do we get for x? 10.4? Is that a rounded 10.4?
Yeah. Or you do it 3 times.
I want to keep it as radical. Yeah. Do we get square root of 108? Yeah. Okay. Now, of course, we can simplify that. For your response, it's not necessary. Okay. So when y equals 6 and x equals 4. And guys, if you use that rounded value, again, make sure you just store that in your calculator, and you always use that full value within the prompt itself, not rounded. Okay. Aren't you all right back there?
Sorry.
I wasn't expecting to. Okay, so we have 2 times root 108. What's my dx dt? 2. Plus 2 times y, so 6. And dy dt is what we're looking for. Equals 0. Okay. Go ahead and solve for dy dt, and let's leave it in that radical. Just in case it was a non-calculator one. Yes? So, we take our derivative and then we're saying, alright, pause. So Brian's pulling the ladder away, and the moment that it hits 6 feet, then we're pausing time and saying, okay, we're using this situation. So we know at that point, my y is 6, my z is 12, and we solve for x. That's what I was doing. So I don't know x, y is 6, and z is 12. And again, that's not true for the whole time, just at that moment. Alright, do we get dy dt as positive or negative? Negative, good. And what do we get? Negative root 108 over 3. Good. Now, if you want to know what the truly simplified version is, that simplifies down to negative 2 3 could work now. Okay. What's our units for this? Feet per second. It's pretty fast.
2, what is that? Oh,
Yeah. What a mean guy.
wait, so they fell from the roof?
I thought
Brian is pushing the ladder away so that she falls from the roof at that speed. I know.
I called a college student.
Alright, so again, let's go and answer the question. Now it says how fast Sasha is falling. They've already indicated that negative amount. So we want to make sure we answer accordingly. Sasha is falling at a rate of 2 root 3 feet per second. Alright, questions with that? Yes?
What do we do knock down if we don't have 2 root 3?
No, if you left it as the square root of 108 over 3, you're perfectly fine. It's for your response. Yeah. You could have left it even crazier than that. Alright, cool. But I like to know the nice things. Other questions before we do B? Again, notice no trig was needed. Okay, so now let's take a look at B. How fast is the angle of elevation of the ladder changing at the same time? Ooh, angle of elevation, gotta use trig. Okay, so let's take a look at our scenario here. Our generic scenario is angle of elevation, theta there. X we said was fixed. No, X is not fixed. Z was fixed. Sorry. And then X and Y were changing. Okay. So it says how fast is the angle of elevation of the ladder changing at the same time? Okay, so let's take a look. We have given to us dx dt, and we know our z value. So keep in mind that when we take our derivative, we're going to have to deal with the rate of whatever variables we're using. So think through sine, cosine, tangent. Which one do you think is going to be best for us to use? Cosine. You guys said that really fast. I thought you'd have to think longer. Cosine? You guys think cosine?
Yeah.
Alright, so cosine of theta would be x over 12. And so when I do my derivative, I have to do with d theta dt, dx dt. Well, looky there, I know dx dt, so that was a very good choice. Okay. So let's go ahead and dive into our derivative. So derivative of cosine. Good job with your negative. Negative sine theta d theta dt. Because once again, derivative of cosine is negative sine, derivative of theta is d theta dt. And over here we just get 1 over 12 dx dt. Okay. Are we good with that piece? Questions on that? Okay. Now let's go ahead and again we're looking at the same time, so when y equals 6 and we know that x was 1 away, right? And let's fill in what we know. Okay, so we have a negative. Sine of theta. I don't know theta, but can I find out what sine is? In this particular situation? So in our particular situation, I feel like I'm like running out of room. In our particular situation, x was root 108, and y was 6, and z was 12. So what's sine of theta going to be? Yeah, 6 over 12 or 1/2. Okay, so we still have a negative, so negative 1/2. D theta dt? Oh, that's what we're looking for. Then 1/12, and the x dt was 2. Alright, go ahead and solve for d theta dt. What do we get? Negative 1 over 3. Do we agree? Okay, let's write in our units before we forget it. Radians per second. Now, again, we didn't have to use cosine. We could have actually used sine since we found dy dt in our last problem. But this was actually a lot nicer than if you used dy dt because you had roots in your dy dt. Alright, so it says how fast the angle of elevation of the ladder changing. The angle of elevation of the ladder is changing at a rate of negative 1/3 radians per second. Or you could say the angle of elevation of the ladder is decreasing at a rate of 1/3 radians per second. Okay, questions on that? Let's try. Yeah. Alright, let's take a look at that plane. They like planes and boats with these types of problems. Batman! This plane. Have you guys seen the Lego Batman movie?
Yeah.
No. The real that.
It's really a good one. I actually watched the real Batman not so long ago.
Which one?
The one where it's like before he's Batman, like shows how he becomes Batman.
Batman Begins?
I don't know. Was that the title of it? I just know that.
In the Dark Knight with Joker and the Dark Knight Rises.
Yeah, those ones are pretty dark. I mean, dark, but they're pretty like mentally draining.
I like the Dark Knight.
Yeah.
Because then he robs the bank. At the beginning, he robs the bank.
Oh, yeah, the school bus.
And you like that part.
No, I don't. No, I feel like Sheldon.
Gotcha. I remember that one. I've seen that. That was a long time. Okay, so Batman's plane is flying west at 500 feet per second at an altitude of 4,000 feet. The plane is tracked by a searchlight on the ground. I think we actually need additional information here. So the plane is tracked by a searchlight on the ground, and the searchlight is east of Batman. If the light is to be trained on the plane, find the change in the angle of elevation, ding ding ding, trig, of the searchlight at the time when the horizontal distance from the plane to the light is 2,000 feet. Okay, so he's flying west. This is my airplane doodad for you guys. Okay, so he's flying west. He's going this way, in case you have struggles figuring out which part of the plane is the person. And we have a searchlight on the ground. Now it says the searchlight is east of Batman, so I'm going to draw the ground. Searchlight is over here. And it is shining. Oh, that. Alright, so the light is to be trained on the plane. And it says that Batman is flying at an altitude of 4,000 feet. So we know that this is 4,000 feet. And it's flying west at a rate of 500 feet per second. Alright, now, is that rate of 500 feet per second going to be negative or positive?
Depends on which way
Remember, a rate should be positive if the distance is increasing, negative if the distance is decreasing. So don't let the fact that we're going west mess with you. Is my distance, so we're talking about that horizontal distance, is my distance increasing or decreasing? It's increasing. So do be careful with that. Even though it says it's flying west, that doesn't automatically mean that it's going to be a negative rate. We have that the distance between the plane, the horizontal distance and searchlight is increasing. So this will be a positive rate. Questions on that? You gotta look out for things like that. Okay. I think it's time to go and put in some variables. So I'm just going to call this x. I'm going to call this y, which is fixed. I'll call this z. So again, it's our dx dt that's changing at 500 feet per second. Okay. So let's see what we know. We have dx dt. It's positive 500 feet per second. Why is that fixed amount? 4,000. And I think that's all we have there. Okay, so we want to think, so it's asking us for angle of elevation. We want to think which trig function is going to be most beneficial for us. Alright, so take a look at what we have. Which trig function should we use? I hear sine and tangent. Talk with your shoulder partner which one you think that should, which one it should.
Yeah, that's a good one.
Either one is a cage.
Yeah, you know, cosine and sine combine.
So,
That's just not true. That's thinking.
So it's the right side, never your side.
I always feel really positive, but then the like things you're on, I get really.
Alright. Give me thumbs up if you think sine. Give me thumbs up if you think tangent. Okay, so it seems like tangent's the winner. Why did we choose tangent instead of sine?
Yeah.
Yeah, they gave us dxdt and y is fixed, whereas for sine, we would bring in z and we don't know dz dt. Okay. Alright, so let's go ahead and use tangent. Oh wait, we forgot to identify what we want. We want d theta dt, specifically when, what's 2000 represent? Yeah, I thought it was something else. Okay, good. When x is 2000. Okay. I did hear that. I hear everything from Alright, so we said tangent. I'm sorry, what did you say? Are you sure? Are you sure? Okay. So we said use tangent, and so tangent theta is equal to what? It is true, it's sine over cosine, but let's make our lives even easier. We have some sides here. Good. Y over x, and we know y is a constant fixed 4,000, so 4,000 over x. Alright, take the derivative. Are we good with that derivative there? Secant squared theta, and then on the right side we get negative 4,000 over x squared dx dt. Good with that? Okay, so now it's just like before. When x equals 2,000, what do we have? Alright, so again, let's think of our situation. We have theta. At this moment in time, x is 2,000. Y is 4,000. Okay. Secant corresponds with which function? Cosine. Cosine. Don't we need the hypotenuse?
Yes.
Go ahead and figure out what is our hypotenuse going to be in this particular situation. Yes.
Wait, so why did you do theta over dt?
Thank you. Thank you. Thank you. Thank you. Oh, how convenient that. It's like it knew. All right. So I lost my d theta dt. Thank you. That would have been a game changer because we would have had nothing to solve for. So guys, the way that you can make your life a little bit easier when you're solving for z here, particularly if it is a non-calculator problem, because you know 2,000 squared is pretty big. So we can think of scaling this triangle down and bring it down by a scale factor of 1,000, so I have 2 and 4, and then solve for z that way. When we solve for z that way, what do we get? Z is square root of 20, which would you guys agree is 2 root 5? So I scaled it down by a factor of 1,000. Now let's scale it back up by a factor of 1,000. So I get 2,000 root 5. Does that make sense there? That can make it a little bit easier to deal with that. Okay. So when x is 2,000, that means that our z is 2,000. Okay. So now once again, we ask ourselves, secant corresponds with cosine. So cosine of theta at this point in time is going to be what? At this moment, what is cosine of theta? What is it? Good. 2,000 over 2,000 root 5. And that's going to simplify to, good, 1 over root 5. Now keep in mind that's my cosine value, so what do I do with it to turn it into secant? Flip it. So it's really just root 5 squared. I don't know d theta dt. Let's see, over here we get negative 4,000 over x squared. Where did x go? X is 2,000. dx dt, and dx dt was 5. Not 5,000, 500. Thanks. Again, if you were required to do this by hand, I would think of this piece here as negative 4,000 times 500 over 2,000. Squared is just the same thing as times itself. Then it's a little bit easier to lop off zeros. So we get negative 20 over 40. You want that? Is that what you guys said? Yeah. So again, if you didn't have a calculator, don't think what's 2,000 squared. Just go and write out this way and simplify. Okay. So all that to say that the whole left side becomes negative 1/2. So I have 5 d theta dt equals negative 1/2. So what do we get for d theta dt? Negative 1/10. And what's our units again? Yeah, that's interesting. Sounds like a weird radian. And again, what we're thinking of with this rate is essentially at that moment of time, our angle is decreasing at the rate of 1 radian per 10 seconds. So not super fast. Okay. Now let's see, what did they ask? Find the change in the angle of elevation. So our angle of elevation changes at a rate of negative 1/10 radians per second. Or if you want to be fancy, the angle of elevation decreases at a rate of 1/10 radians per second. Questions? Bart, is that a question?
Yes. The 2000.
So we're looking at the moment when x is 2,000. So if this is our point in time when x is 2,000. My y value is a fixed 4,000. So Pythagorean theorem solving for this here, or I said a little bit of an easier way is if we scale it down by 1,000. We have a 2, 4, and then solving for that using Pythagorean theorem we get 2√5 here. So then scale it back up by 1,000. So I divide by 1,000, multiply it back up by 1,000. Use that. Was there another question?
Yeah. Are we allowed to have radicals in the denominator or no?
Yes. Calculus you can. No complex fractions.
Okay.
And you must evaluate truth. Those are kind of two main things for fractions.
Okay.
Alright, other questions with that? Okay. So I want you guys to go ahead and try example 4. Our buddy old boy, old pal Daniel. And again, feel free to work with one another on example 4 here. Focus part. God bless you. All right, pause and talk to your shoulder partner. What's the equation you're using for this problem? So talk to your shoulder partner. What equation are you guys using?
Makes sense.
All right, what equation are we using?
Pythagorean theorem.
Pythagorean theorem, right? Are we doing anything with the angle? No, so don't force the angle if it's not needed. Pythagorean theorem, good. I just want to make sure no one was out there slaving away at tangent theta equals Alright, so carry on. I'm gonna go and start filling in information so you can kind of compare. I love that the derivative constant's here because I always start to get worried like, oh no, 120 squared. I'm like, no, we're doing the derivative. It doesn't matter. Yes. Yeah. Because otherwise, what you're doing is you're saying that equation is true all the time. Like when you start putting the numbers, what you're essentially saying is up here. What you're saying is d theta dt is that all the time. I'm going to specify it's that one time. It's kind of like the notation. Where we would say like x equals y equals. But since it's an implicit, it's not so easy to write it that way, so we just specify one. Yes. Because it should be.
Good afternoon, please press
Oh,
interruption.
yeah, because we're looking
There
at
will
the
be a
moment.
girls' soccer interest meeting on Thursday, February 8th at 3 p.m. in the lecture hall. There are a number of unclicked items along the sound.
So why
Please
is
check for
120?
any
It's 120
items
feet
in the
above the ground.
All unclicked items will be donated to
This
the meeting
represents
club.
the
Thank you
string.
and have a great afternoon.
So at the moment, because the string's going out, then at the moment that's 150 out. That's what we're looking at.
Okay.
So we're going to use the 150, the 120 to solve for x. Does that make sense? All right. Did anyone get 18 feet per minute?
Yeah.
Oh, good. Okay. So your homework is to finish these trig-related rates. So you have what? One more kite, and then we've got our free response AP questions. Remember, keep in mind if your distance is getting smaller, that's a negative rate. If your distance is getting bigger, it's a positive rate. Yes.
Extra problem. I think should be when we go second.
No, they're saying what's the rate of change when the angle is pi over 6. So they're not saying the angle is pi over 6 the whole time. They're saying what is the rate of change on the angle at the moment the angle is pi over 6. Does that make sense? I know it's drawn in the picture, and I don't like that because it makes it feel like it's given. Alright, so again, as you do these problems, I recommend for the first response, set a timer 15 minutes, see what you can do, then grade it according to that grading rubric on Google. To be determined. Wait! I won't see you guys for a long time. Have a good long 5 days or whatever it
Wait
is.
the leadership hour when I helped you.
Yeah.
Thank you. I really needed to get
What'd you say,
A in
Mark?
class.
What?
We don't see you tomorrow.
Is that
Why
a
is
good
that-
thing? Bad thing?
Like, why are we laughing at
We
that?
always do stuff in this class, so it is.
Oh, it would have been us. Oh, I see.
Oh,
Next time.